Did you hear that the fish scientist quit his job at the deep sea clinic? The pressure got to him because there's a lot of pressure deep underwater. All right, seriously. So there is a lot of pressure far beneath the ocean waves, and anybody who wants to dive too far down needs to be ready for it, on the way down and on the way back up. We're about to get into why coming up from the deep is more complicated than simply letting buoyancy take over, and how deep sea divers avoid getting into bubble trouble. You ever been diving before, Mitchell?
I have not. I try to stick to climbing up mountains, not diving in oceans.
Yeah, fair. I'm not built for the water either. I think I tried snorkeling one time in Cuba, unsupervised, almost drowned, but I think I saw a couple of fish, so worth it.
That sounds terrifying.
Yeah, it was kind of scary. But I've always thought as a kid as well, and I toyed with the idea of if we wanted to explore the deep sea oceans, why don't we just get like a really long hose, go down there, breathe through the hose, which is basically a really long snorkel. But then I realized that's probably not the best idea.
Yeah, you would probably get crushed.
Yeah, crushed like a panini. But the thing is, in hospitals, we do see people come in, especially divers, with certain changes to their lungs and manifestations and symptoms. And I think that's really cool because it is something that we actually have to treat in healthcare.
And there's actually a fair amount of folks who come through the hospital with what we call barotrauma, which is exactly as it sounds: baro, pressure, and trauma, damage. So physical damage to the body being caused by differences in pressures between a individual's lungs, individual's body, and the outside environment.
Right, and I can imagine if it stretches a little bit too far, if it collapses too much, that's where we can really start to see those symptoms manifesting.
Yeah, exactly.
Yeah, even from a milder form, I like to think of barotrauma as in our ears, we have something called aerotitis or barotitis, which is like if you go up in an elevator or you go in a plane, when you're rising and you're landing, you feel that popping in your ears, right? When you swallow, it's really just pressure changes and you have a really thin canal between your nose and your ear. We call that the eustachian tube. And when that's blocked, and then when it suddenly opens, those pressures equalize again, and we hear that pop, we feel that pop.
So another consequence of these pressure differences is called decompression sickness, which again, decompression, it's if you change your pressure from being very pressurized to a lot less pressurized too quickly. You may have heard this also called the bends,
right,
or diver's disease. And it's a medical condition caused by the dissolved gases in your blood and in your body emerging from the solution that they're dissolved in into their gas form.
Sounds wild.
Yeah. While DCS is most commonly caused by ascent decompression during underwater dives, it can also be caused by other depressurization events, such as emerging from a caisson, flying in an unpressurized aircraft at high altitude, or performing a spacewalk on a space station.
So just some everyday things, you know?
Right.
So I guess the question then becomes, where do these bubbles actually come from, right? They decompress, what actually happens? And so part of it's the air that they breathe. When divers go down, they have to breathe these special solutions, these special air mixtures. And part of these mixtures is they add in inert gases like nitrogen and helium to increase that pressure without really changing the concentrations of everything else. The issue is that when you increase the actual pressure, you end up dissolving more of these gases into the blood, and that's when you rise too quickly, it wants to dissolve back out and form these bubbles.
So when we have those bubbles form, it has two primary clinical manifestations. One of those is DCS1, in which you see dermal, musculoskeletal, and lymphatic involvement. And the other is DCS2, where you see CNS involvement, so your nervous system. In DCS1, you can have things like rashes, itchiness, or joint pain. Whereas in DCS2, you get things like confusion, numbness, and tingling, and that can progress all the way to seizures.
And so this is why divers need to be so careful about controlling the way that they ascend and descend, because you go too quick, it's going to cause a problem. We can't help but wonder, though, with all that equipment on them, isn't that going to weigh them down? But the reality is they have a special piece of equipment called the buoyancy compensator, which actually helps them control their buoyancy to raise their ascension a little bit faster or slower and control that as they go.
Yeah, absolutely. That compensator works to establish a neutral buoyancy between the scuba diver and the surrounding water. And the way that this works is that compensator contains pressurized gas that is then used to fill up a bladder. And that bladder then increases in volume and decreases the density of the scuba diver with the compensator.
So I'm really glad that you brought up density because that's really the foundational principle behind buoyancy. Density being just the amount of stuff per volume. And if we think of it conceptually, if something is more dense than its solution, it'll sink. If something is less dense, then it'll float. And if we think about this with soda cans, even just Coca-Cola, if we think about regular Coca-Cola, it has about a density of 1.11 grams per milliliter, whereas Diet Coca-Cola, it's about 1 gram per milliliter.
So if we assume that we have two 355 milliliter cans and that they are fully submerged, we'd be able to know that the buoyant force is equal to the gravitational force in the case of the Diet Coke. It's not moving up or down, it's neutrally buoyant. But in the case of the regular Coke, the gravity is greater than the buoyant force, causing the can to sink.
And I think this is a really interesting point because when I was learning about densities and buoyant forces as well, I always thought about how is it in this case we have two cans with different densities, but they technically have the same buoyant force. And so if we look at the actual equation, the buoyant force is rho, so our density, times the volume, times gravity. But both the rho and the volume are actually relative to the fluid displaced. And so in this case, because it's the same water in both cases, the buoyant force will be the same because it's the same volume displaced and the same density displaced. And so I like to think of buoyant force almost like the water trying to come back into that space that's been displaced. It's trying to push its way back up. And that's ultimately why the buoyant force tries to push up, whereas gravity is trying to pull it down. So with this principle, the idea of buoyancy is really, for an object to float, it has to either displace enough fluid to create a buoyant force equal to its own weight, or it has to have a fluid with a higher density that with that given space, it just has more push to it because there's more stuff there.
So our next question might be, how can we make that regular Coke can float? And if we take a look at the equations, and we take a look at what our current buoyant force is, we would see that it's rho, our density, times volume, times our gravitational constant. So 1 gram per milliliter times 355 milliliters times our gravitational constant is going to be 355 grams times our gravitational constant. Now, when it comes to our gravitational force, we already know that for the Diet Coke, it's going to be about equal to that buoyant force. But in the case of our regular Coke, we actually have a greater density of that Coke. We've got 1.11 grams per milliliter. That results in a gravitational force that is 394 grams times our gravitational constant. So that tells us there's kind of an imbalance between our gravitational force and our buoyant force. So in order to balance that out, the only way we can do that would be to increase our buoyant force. And to do that, like you were talking about before, we need to increase that volume in order to increase the buoyant force.
So it's that exact principle that they can then use in buoyancy compensators to increase a volume, decrease a volume, to change that respective density, allowing divers to go up and down respectively, right? But if we bring this back to decompression sickness and barotrauma, where does that actually come from, right? Where does that pressure from the environment even come from? And I think the key to understanding that is really just understanding hydrostatic pressure. Hydro being water, static being it's not moving. So just a water column. And so the formula for that is going to be P, our pressure, is equal to rho, the density of that fluid, times G, the pull on that fluid, and times H, the height of the water column. And so it makes sense according to our equation that the deeper you go, the more pressure you have. And I think it's actually every 10 meters that you go below sea level underwater, it becomes one more atmosphere pushing down on you. So no wonder why if you go deep into the water and you open a little hose up to the atmosphere, that's going to crush you real quick.
Absolutely. And it's that increase in pressure that makes it harder to breathe. Remember that our thoracic cavity needs to expand for the air to get into our lungs. So to compensate for that, divers breathe pressurized air that is equal in pressure to the diver's surroundings. This keeps the lungs able to inflate. So let's think about those soda cans again. But this time, let's think about that carbonation that gives them their fizziness. How do we actually manage to dissolve all that CO2 in the can? We got to pressurize it. And then what happens when we open up that can, the fizziness comes out, right? All that gas escapes in the form of bubbles. And the air that scuba divers breathe isn't really different than regular air, and it's actually a lot like the situation we're talking about with our soda cans. That increased pressure allows more of that gas to be dissolved into the blood, and specifically nitrogen. And if the diver ascends too quickly, we're pretty much opening that soda can, and all those bubbles come out into the blood vessels, which can cause a bunch of problems.
Yeah, I think of that. I don't know if you did that experiment in school with like the crystal thing. Like you put a little string in super saturated crystal sugar water and you got like crystal candies from it. But it's similar here where when you increase the pressure, you're really just dissolving more gases. They become more soluble. And so for divers, if they come up too quickly, that gas is no longer soluble. And so it crashes out a solution in the form of bubbles.
And that's exactly why scuba divers need to go through decompression stops. And at those stops, they wait at a certain depth and for a period of time in order to allow their body to acclimate to the lower pressure. So that you're not opening the can of soda all at once, but just letting it slip out.
Yeah, a little bit at a time. Right? And then besides the actual blood and like bubbles in your body, you got to think of your lungs too. And we talked about barotrauma earlier, but this idea of sudden pressure changes can really impact the health of your lungs. And let's just hypothetically say we go down 50 meters below water. All that pressure is squeezing in on us. Like you said, we're breathing pressurized air to help keep things balanced, to make sure we can inflate our lungs. But then if you start to hold your breath, they teach you this in diving school. They say never hold your breath. If you hold your breath and you start coming up, because you're decreasing in height through that water column, the pressure around you decreases. But the pressure in your lungs is still pushing against the walls at that original pressure, right? And you can imagine if we're 50 meters down in the water, that's 5 atmospheres pushing down on you. Your lungs are also pushing out at 5 atmospheres. So if you come up too quick, your lungs are pushing out at 5 atmospheres. That doesn't sound like a fun situation.
Absolutely not.
Okay, so we're diving, we're going down deep, we're going down, we're coming back up, and then a bunch of bad things start happening.
Yeah, and your lungs essentially behave like a balloon. You got too much pressure in that balloon, it can pop.
Gosh, that's brutal. You want to grab a soda?
To decompress?
Hey!